Hello again. Welcome to the 13th episode of this series on mechanics. Our exploration of how these intriguing mechanical quantities can help us understand the world around us. Even if we restrict ourselves to quantities with space and time exponents that are small integers, we've seen that we get a fascinating bunch of players. Within the dynamical paradigm adopted in this series, the incredible diversity of natural phenomena results from the interplay of these characters. Space, time, and motion are the music they sing. We've tried to analyze this music by decomposing it in themes, by isolating duos, pairs of mechanical quantities, horizontal pairs underlying sizes, lengths, distances, vertical pairs for time, durations, periods, diagonal pairs for motions of all sort. Since episode 9, we've introduced trios. When these trios are not aligned, we've seen that they produce events, space-time points where the regimes from the three pairs of the trio intersect. These events are turning points of the dynamics and provide objective units, regardless of the kinematic perspective. In the last episode, we talked about horizontally aligned trios, which provide a mechanical underpinning for geometry. The trio contains three pairs that produce three associated simple lengths. Although the mathematical structure of this relationship is quite simple, the connection has only been made sporadically in the existing literature. In the last episode, we outlined various aspects of this link between geometry and mechanics. We saw in particular how the relative magnitude of the three lengths reflects the positions of the mechanical quantities. The three lengths produced by such trio are connected by a geometric identity. A naive dimensional approach would be at loss to explain such relationship. The value of the exponent alpha would remain indeterminate. If we, however, know the mechanics underneath the geometry, the value of alpha is a simple consequence of the positions of the mechanical parameters. It changes as the mechanical factors move. Every horizontally aligned trio is associated with a single geometric identity. Identities like that are everywhere, but places where the underlying trio has been fully identified are rare. So we invite you to go hunting for these geometric relationships and to find their mechanical justification. Today we'll talk more about these horizontally aligned trios, but we will also address the more general case of any aligned trio, which also produces three parallel lines in the kinematic plane, not horizontal, but diagonal, a reflection of the slope in the mechanical plane. Just as we saw in the last episode, the line in the middle is always the one built from the extremities of the trio. The line closest to it is built from the most distant remaining pair. The last line is from the last pair. However, we do not know a priori the full ordering of these three lines, if the red one is larger than the violet and blue, or the other way around. It is the values of the mechanical quantities that set the ordering, through a dimensionless number that we've called the index. The index dictates the ordering between the parallel scalings, and as we mentioned in the last episode, its value, greater or smaller than 1, defines two qualitatively distinct modalities of the trio. Any trio is dual, and today we'll try to get a better feel for what this duality means in practice. Let's start with our first example concerning the distinction between viscous and inertial dynamics of droplets and bubbles. We've encountered these kinds of dynamics on multiple occasions. Depending on the situation, we've seen how surface tension, viscosity, and density could have an impact. In episode 10, we also saw how to convert the droplet or bubble size into a Laplace force. Today we ask about what to expect when considering this force in addition to the viscosity and density of the droplet, or of the surrounding fluid for bubbles. These three mechanical quantities are aligned in the mechanical plane. We already know all the pieces of this puzzle. We saw the first regime for the first time in episode 6, and in more detail in episode 10. We know that this regime can be used to describe the coalescence of bubbles and droplets in very viscous outer fluids. The second regime is Rayleigh's regime. We've talked a lot about this one, also in episode 10. It governs some pinching bubbles in low viscosity fluids, as well as some coalescing and spreading droplets. The third regime gives the dynamics of laminar boundary layers, introduced in episode 6. The three regimes are diffusive, in the sense that they all have a size proportional to the square root of time. The three quantities are indeed on a diagonal of slope negative 1/2. So from the canonical perspective, we see three parallel lines in the kinematic plane, with a slope of 1/2. In the middle, we have the furthest pair from the trio, force and density. We can see this more clearly by using the constant variable common to these three regimes. We've seen this kind of selection of the right angle in episode 8. Here, the constant variable is a diffusivity. From the canonical perspective, we got square roots, but if we square both sides and put the variable time on the left, we get three constant right-hand sides, each given by the ratio of a different pair of mechanical quantities. To facilitate comparison with the case of horizontal trios, we can introduce symbols for the three constant diffusivities. These three diffusivities are connected, just like the simple lengths before, but they follow a kinematic rather than geometric identity. The diffusivity built from the force and density is the geometric mean of the other two, so it is indeed in the middle. Just as for the lengths, the gaps in the kinematic plane are the same because the gaps in the mechanical plane are the same. And just as before, which diffusivity is larger or smaller will depend on the values of the underlying mechanical quantities. Let's consider a great example of this trio at play: the coalescence of air bubbles in increasingly viscous silicon oils. The radius of the neck between the two bubbles is plotted over time, starting at the instant of contact. These experiments were published some time ago, in 2014, by Paulson and co-workers, but in our opinion, they remain the best illustration of the duality of the trio of force, viscosity, and density. How can we use this trio of mechanical quantities to understand what is going on in the kinematic plane? For all the coalescence dynamics represented here, the neck radius is quite close to a square root of time. In other words, these dynamics are diffusive, each characterized by a different value of the diffusivity nu. We can better assess the agreement with this scaling by adopting the right angle on these dynamics, plotting the square of the neck radius divided by the time, such that each plateau gives a value of the diffusivity. Note that we still use the time as horizontal axis, but we may use any kinematic variable we want, and in particular the neck radius itself. From this perspective, we can better understand the eventual departure from the diffusive scaling. Eventually, the neck is bounded by the size of the bubbles, here around 1 mm, and so its motion must stop there. We've talked about this transition in episode 10, so we will disregard it today and focus on the earlier dynamics. There, how can we understand the observed values of diffusivity? What mechanical quantities are they depending on? For most curves on this plot, they do seem to depend on the viscosity, but not for all. The plateau at the top is actually made of three different experiments. One with an outer fluid with a viscosity of 9.4 millipascal/second, one for 0.82, and one for 0.49. All have a similar diffusivity. So in this range, viscosity does not affect the dynamics. For each experiment, we can record the diffusivity and plot it against the viscosity of the outer fluid. For coalescence in viscous enough fluids, the diffusivity seems to be inversely proportional to the viscosity. The diffusivity has the dimensions of an area over a time, and the dimensions of the viscosity are ml-1, t-1. So necessarily, the coefficient of proportionality has dimensions m, l, t-2, which are the dimensions of a force. In this range of viscosity, the diffusive dynamics of the neck are governed by a dynamic duo, where the impelling factor is a force F, and the impeding factor is the outer viscosity It. Fitting the data gives a force around 1.7 10 to the minus 5 newtons. Where does this force come from? We know this since episode 10. It is the Laplace force, which if necessary can be expressed as the product of the surface tension gamma and the size of the bubble L. In all these experiments, as already mentioned, this size is fixed, around 1 millimeter, and the surface tension only varies slightly. Using these values, we indeed recover the observed behavior, the thickness of the line reflecting the range of surface tension. So we've identified 2 out of the 3 mechanical parameters. What about the third, density? Can we use it to understand the change in behavior at low viscosity? There, the dynamics are independent of the viscosity. Let's recall our 3 regimes. We've just seen the first one. Can the second one explain what is seen at low viscosities? It is the only one that does not depend on the viscosity. Let's try. For these 3 data points, the force only varies slightly between 1.5 and 1.9 times 10 to the minus 5 newtons. The density of the oil surrounding the bubbles is between 760 and 935. Taking the square root of the ratio of these 2 mechanical quantities, we get an estimate for the resulting diffusivity. The agreement with the data is not perfect, but it can be fixed by adding a numerical prefactor around 2. When we translate back this regime to the canonical perspective, we see that the prefactor remains fairly close to 1, which has been our provisional criterion to assess the validity of a regime, until we can formalize this more rigorously in future episodes. So this mechanical trio might indeed underline these dynamics, separated in 2 regimes. One governed by force and density, and another at higher viscosity, governed by force and viscosity. But where is the third regime combining viscosity and density? If we want to strengthen our belief that this mechanical trio really underpins these dynamics, we have to represent the data more objectively. Right now, we are still using subjective units for the diffusivity and viscosity. We can do better than that. We should do better than that. Here, we've been able to notice the existence of 2 different regimes, because these experiments all share the same bubble size, and all the fluids have fairly close values of surface tension and density, so the data points all fall on the same 2 trends, since the force is always fairly constant, and the density too. The only parameter that significantly varies from one experiment to another is the viscosity. If we start to vary all parameters, we are going to get a more scattered plot. A lot of these new data points have the same viscosity, that of water. The filled disks correspond to coalescence of bubbles, the same kind of setup studied by Paulson. Also included are the diffusive dynamics that some pinching bubbles exhibit. A number of experiments on the coalescence of droplets, with slight variations in protocol, and some data points for spreading droplet, either onto a plate approached from above, or deposited on a substrate. We've already encountered all these experiments at one point or another since the beginning of this series. What we want to know now is if they can be understood with the trio of force, viscosity, and density. Obviously, most of the new data points do not fall on the 2 regimes we drew from Paulson's experiment. And this is not surprising since the values of the mechanical parameters vary from one experiment to another. For example, for a 2 millimeter drop of water, the values of the force, the viscosity, and the density would predict these lines. We know what we have to do. We have to properly scale the axes. That is, we have to find objective units. Let's start with the diffusivity. For any data point, we have a value for the force, the density, and the viscosity. And we know that from this trio we can produce 3 units of diffusivity. These 3 units are equally valid. Let's try them one by one. First, the unit based on force and viscosity. Unsurprisingly, with this choice of units, Paulson's experiments in viscous outer fluids do not fall far from one. The other data points remain pretty scattered. Alternatively, we can try to scale by the kinematic viscosity, the diffusivity based on the viscosity and density. From this point of view, whether or not the observed diffusivity is smaller or larger than the kinematic viscosity seems to distinguish the viscous and inertial regimes we had seen in Poulsen's data. But the rest of the data remains scattered. Finally, we can use the unit based on force and density. Dynamics on this purple line are those that strictly follow Rayleigh's regime. The coalescence experiments in low viscosity fluids by Poulsen suggested that a numerical prefactor could be needed, but this correction is evidently not universal. If we pick a different point, we get a different correction. But how can we be sure that any given point is in the inertial regime rather than in the viscous regime? Take this other point. How can we know if it is in the viscous or inertial regime, or even somewhere else? To answer this question, we have to rescale the viscosity axis. We've only done half of the work here. We've drawn one out of the 3 scaling laws we get from the trio, the trivial one in these units. We've got 2 other scalings. If we express these scalings in the same objective units, we get 2 similar results. These ratios are dimensionless. So the square root of a force times a density must have the dimensions of a viscosity. This combination of force and density provides an objective unit for the viscosity, to replace the convenient but arbitrary international standard. With these fully objective units, the 3 scalings of the trio intersect at the point where the scaled viscosity is equal to 1. If we add the data, we now have an objective way to distinguish viscous and inertial dynamics. But a lot of questions remain unanswered. Let's try to address them one by one. First, although both axes of this plot are dimensionless, these dimensionless numbers are fundamentally different. The vertical axis is a simple dimensionless number. It is the constant variable of the regime combining force and density, given in objective units. You can check that it corresponds to the square root of the simple dimensionless number as defined systematically in episode 8. It is a fine unit, but there are 2 other choices. The simple dimensionless numbers of the force and viscosity regime, and of the viscosity and density regime. In that case, the dimensionless number on the vertical axis is quite famous. It is called the Reynolds number. So we have 3 equally valid dimensionless numbers for the diffusivity axis, but in contrast, the dimensionless number on the horizontal axis is unique. It is not built from a pair of mechanical quantities and a kinematic variable, like the simple dimensionless numbers. It is rather based solely on mechanical parameters, the 3 elements of our trio. It is the index of the trio. Like any dimensionless number, it is defined modulo an overall power. You can check on your own that the only way to build a dimensionless number from these 3 mechanical quantities is indeed to group them in this way. The choice of overall power is arbitrary. For any aligned trio, the convention that we will adopt is to choose an exponent gamma such that the mechanical quantities have the smallest integer exponents. This leaves us with this possibility, or its inverse. We'll choose this one, and more generally, for any aligned trio, we'll put the middle quantity in the denominator. Here it's the viscosity. This dimensionless number is also quite famous. It is called the Laplace number. Written in this way, the index of the trio can be understood as a force scaled by viscosity and density. You can check that the square of a viscosity divided by a density is indeed a force. Another way to think about the Laplace number is as a density scaled by a force and a viscosity. If we were to plot the scaled diffusivity versus the density for each experiment, we would get a pretty depressing result. Except for this one example concerning drops of mercury. All other fluids used have a density not far from that of water. On a plot like this, it would be hard to even see 2 different regimes. But the density is given in kilograms per cubic meter. And these arbitrary units are convenient standards for us, but they mean very little for droplets and bubbles. Most of these fluids have a similar density in these subjective units, but if we scale this density by the viscosity and force relevant to these droplets and bubbles, then, well, we recover something familiar, where two regimes are clearly present. Although the fluids may have first appeared to have similar densities, when these densities are properly scaled, they range over 12 orders of magnitude. So the index of the domain can be thought of as the objective density for these drops and bubbles. And as we've seen, another possible approach is to invert the square root of this number, to get a scaled viscosity. Written in this form, this dimensionless number is called the Ohnesorge number. Usually the force is expressed from the surface tension and the droplet or bubble size. Presented like this, or like that, this index is essential to understand the trio it comes out of. This objective plot is certainly better than the subjective version we started with. We may now understand why a change in the dynamics may occur when the index is equal to 1, but it is unclear what goes on some of the branches of this star. Are these trends somewhere in the dynamics? But we are not looking closely enough. The data points on the graph solely track the dynamics of a radius, for instance, the neck between coalescing drops. If we only track how this radius changes over time, we notice that it only follows two branches of this crossroad. But there is more to a coalescence than the evolution of the contact radius. The shape of the neck may vary from one condition to another. Waves may be traveling at the surface of the drops, and the coalescence is associated with a non-trivial flow inside the drops or outside the bubbles. If we were measuring these additional motions beyond the contact radius, would we be able to populate some of the other branches of this plot? For instance, we know that the red scaling corresponds to pairing viscosity and density. We've seen this scaling in episode 6 in the context of boundary layers. Wouldn't we be able to find places with similar velocity gradients, boundary layers, if we were to take a closer look at the flows associated with such coalescence? Going back to the data we have. Some scalings on this plot may seem superfluous, or maybe it is our way to represent the dynamics that is partial. We encountered a similar question when we discussed non-aligned trios and the associated events in episodes 9 to 11. There, the plots were firmly in the kinematic plane. There were several ways the dynamics could go at the intersections, but only a few paths seemed to be followed. We're not ready to fully understand what is going on here, but we're starting to better grasp the issue. For an aligned trio in the mechanical plane, we do get an intersection, but not in the kinematic plane anymore. Here, the vertical axis is kinematic, but the horizontal axis is mechanical. Several branches connect, but only a few seem to be observed. There are no already existing rules on how to understand this, so we'll have to figure them out as we go. And the difficulty is not specific to kinematics, it was already there in the last episode, when we discussed geometry. For instance, it was already there when we discussed the shape of single cells on soft or stiff substrates. Let's say a few more words about this example before we move on to our last case study. The analysis of experimental data on the volume, height, and contact radius of cells in the last episode suggested that this trio might provide a satisfying mechanical model for the shape of single cells spread on substrates with different values of elastic modulus sigma. Gamma was some stiffness or surface tension, or adhesion energy per unit area. We did not have enough data to conclude. And a third unnamed quantity Q, required by the way the height and contact radius scaled with the elastic modulus of the substrate. In this plot, both the vertical and horizontal axes are given in subjective units, the meter and the pascal. We can of course use any one of the three simple lengths as our unit. In particular, we can use what we called the bulk radius in the previous episode, the length constructed from the volume of the cells. With this unit, the vertical axis is now objective. What about the horizontal axis? Well, just as in the case of drops and bubbles, in this plane, the three simple lengths eventually intersect. There is a special value of stress where this happens. And just as in our first example, we can use this special stress to scale the horizontal axis. The value of this special stress can be expressed mechanically by equating any pair from the three simple lengths. Naturally, these three equations give the same result: a stress that is independent of the elastic modulus of the substrate, and that depends on the two other relevant mechanical quantities. Thus, the horizontal coordinate of this plot combines all three mechanical quantities. This axis is a power of the index of the trio, here defined following the convention set for the bubbles and drops, in such a way that the factors have the smallest possible integer exponents, and with the middle quantity in the denominator. This plot of the relationship between the shape of cells on substrates with different elastic moduli is actually similar to this plot of the relationship between the diffusive kinematics of drops and bubbles with different viscosities. However, in this example, experimental measurements only fell on a few branches, whereas here, measurements of the height, contact area, and volume provide data on all three branches. But what about here, on the other side of the intersection? Looking back at our first example, we may expect a change in behavior. Here, the diffusivity was dependent on the index on the right, but independent of it on the other side. The value of the index, greater or smaller than 1, defined two modalities. What about now? In the previous episode, we had neglected results on the softer substrates, but we can now add back the data. When the elastic modulus is smaller than the critical modulus, the radius, the height, and the bulk radius, and so the volume, are independent of the substrate. But the three trends do not exactly overlap. Because on soft substrates, the cells are not exactly spherical. Their volume is only approximately given by the formula for a sphere. There is actually a numerical correction, a delta, related to the contact angle of the cell with the substrate. We do not wish to get into the details here, but such numerical factor is responsible for the slight offset, not unlike the offset we saw in the first example. If these subtleties were more properly taken into account, the data would more clearly reveal their inherent duality, with two qualitatively different regimes. On the right, the index is smaller than 1, on the left, larger than 1. The value of the index distinguishes the regimes of soft and stiff substrates. A more complete model would seek to better understand the mechanical factors of the threshold in substrate modulus, to comprehend the origin of the stiffness, gamma, and to interpret the mysterious quantity Q. How would the values of these quantities vary from one cell type to another, by changing the osmotic pressure, or by altering the cytoskeleton? These are fascinating questions, but they are beyond our scope today. Our goal was to get a better feel for this new kind of dimensionless numbers, the indices, and this example, or this one, are just one out of many, where an index can be built from an aligned trio of mechanical quantities, either diagonally or horizontally. We leave it to you as an exercise to find examples of indices built from vertical trios, like this one, a famous trio that can be used in the context of damped oscillators, where m is the mass, gamma the stiffness of the spring, and zeta the friction that progressively damps the oscillations. We invite you to relate the index of this trio to what are called the damping ratio and the Q factor. We also invite to explore other trios. Not far is this one useful in rheology, or this one, which we suspect would be useful in the study of turbulence in viscoelastic fluids. Rather than investigate vertical trios, we would like to end this episode with another example of horizontal trio useful to the study of craters. The physics of cratering is quite rich, and so what we'll talk about will only concern a small fraction of it, the part governed by the interplay of three aligned mechanical quantities: an energy E, a stress or elastic modulus sigma, and a weight density psi. We'll see how this trio could help us better understand craters, those produced by explosions, like the one we are seeing here, or by impacts, like this one. In episode 2, we talked about these two examples. The one on the left is the crater left after the nuclear explosion we just saw, the Sedan crater. The example on the right is meteor crater, and as the name suggests, it was produced by the impact of a meteorite. Although the formation process was different, the result is at least superficially similar, a fairly circular depression in the ground. Now that we are dabbling in geometry, we could ask about the size of the rim, the slope of the depression, or its depth. But the most obvious geometric metric is probably the projected area of the crater, or equivalently, the mean diameter, or radius, which we'll provisionally call L. The Sedan crater has a radius around 200 meters, and Meteor crater is 3 times bigger. Back in episode 2, we claimed that the radii of craters could be understood from the ratio of the energy of the explosion, or impact E, and the weight density psi of the lifted ground material. We'll here nuance this claim. For the Sedan nuclear test, the reported yield of the explosion was 104 kilotons of TNT equivalent, so around 4 times 10 to the 14 joules. Facing the energy is the weight density, product of the density ρ of the ground material and the acceleration of gravity g. The explosion occurred in an alluvial deposit with a density around 1.8 grams per cubic centimeter, so overall psi is around 17,000 newtons per cubic meter. The ratio of these two mechanical quantities is around 210 to the 10 meters, to the power 4, and so the associated length scale is around 400 meters, 396 if we want to profess a precision we shouldn't really claim to have. 'Cause 396, or 400, that's not the same as the measured radius around 200 meters. The length scale we obtain is an order of magnitude, and we don't know a priori if this order of magnitude will match the radius or the diameter, which are equally valid metrics. Based on the numerical comparison, it seems that the computed length L may actually be the diameter, but that could just be a lucky coincidence. The validity of a scaling is not based on a single example, but on many. For meteor crater, the energy of the impactor is not known with precision, so the only thing we could do is to estimate it. By comparison with the Sedan case, the size L should be the diameter, so around 1.2 kilometers. The weight density similarly depends on the density of the ground material. But the crater is so large that several layers of mudstone, dolostone, limestone, and sandstone were excavated, with densities ranging from 1.6 to 2.8 grams per cubic centimeter. So the energy of the impact estimated in this way should be between 3 and 7 times 10 to the 16th joules, or roughly 10 megatons of TNT equivalent, which, unsurprisingly, matches the official estimates, since they were typically computed using the same hypothesis, namely that the physics of the meteor crater are similar to those of an explosion crater like Sedan. The size of the crater is due to the balance between the energy and the weight density. Whether the energy comes from a bomb or from the kinetic energy of an impactor seems to be irrelevant. In these two cases, the comparison may be valid, but extending it blindly to other examples is a risky gamble. There is a number of factors that could end up breaking this scaling in some circumstances. We'll consider just one such factor, the characteristic modulus of the ground, sigma. The scaling for the crater size at the bottom is independent of this elastic modulus. How could that be? Shouldn't craters in jello be different from those in steel or even diamond? Let's try to approach this situation in the context of what we've learned in the last episode. We have 3 mechanical quantities: an energy, that of the impactor or explosion, a force density, the weight density based on the density of the ground, and we now have a stress, an elastic modulus of some kind, characterizing whether the ground is soft or hard. That's 3 quantities on the same line. The perfect mechanical framework to be talking about geometry. From these three mechanical parameters, we can build three simple lengths. These lengths are connected by the following geometric identity. If we only had a naive view of geometry, such four-dimensional equation would be quite troubling. We would be at loss trying to identify an object for which the volume in 4 dimensions is given by the product between a 3D volume and a length. A sort of 4-dimensional cylinder, if you wish. But we know better now. The lengths associated with a mechanical trio are not always apparent. Some may be readily observed while others remain hidden, as in the example on trees in the last episode. Then two of the three lengths could be seen. They were the height and radius of trees. And the third length was hidden. It was actually the same kind of simple length we have here, based on an elastic modulus and a weight density. Will this length remain hidden as well in the context of craters? What about the other two lengths? For trees we could see both a radius and a height. So for craters, should we assume the first length to be the radius and the second, maybe the height of the crater? Let's start with an idealized setting. An astronomical body like the Earth, but approximated as a ball made of a single material. This ball is held together by gravity in such a way that its size is given by the hydrostatic equilibrium, based on its modulus sigma and the weight density connected to its density ρ and surface gravity g. Since we don't really need too much precision, we set g around 10 meters per second square, and the average density of the Earth is around 5.5 tons per cubic meter. The radius of the Earth is about 6,400 kilometers. So if we want to avoid dragging around a numerical correction, we can just set the value of the effective elasticity so the values match. In this case, we would get a modulus around 350 gigapascals, which is typical for hard metals. Now then, we have an understanding for one of our simple lengths. It is the size of our testing ground, the astronomical body on which we want to study craters, made by explosions or impacts. These events are idealized as the almost instantaneous release of an energy E. There is, however, a major difference between a bomb and a projectile. The projectile can only hit the surface of the object, whereas the bomb could be buried. Let's go there, deep within the planet. We've seen before, in episode 2 and in the explosion series, that deep underground explosions carve out cavities in the surrounding ground. The size of the cavity depends on the energy of the explosion and on the modulus of the surrounding medium. We call this radius R2, so as not to confuse it with the radius of the planet. Here, the elastic modulus is that of the planet, and if we neglect numerical corrections, the formula would predict cavities of 2 meters for 1 ton of TNT, 20 meters for 1 kiloton, and 200 meters for 1 megaton. Because of the cubic root, multiplying the energy by 1,000 only multiplies the radius by 10. So the size of the cavity increases rather slowly. But eventually, if the energy of the explosion is large enough, the whole planet could be blown to pieces. We have to compare the radius of the cavity with the radius of the planet. The game is over when they are equal. For a given planet, the elastic modulus sigma and the weight density psi are fixed. The only variable is the yield E of the explosion. So we can derive the critical energy over which the planet will be no more. As an exercise, you can show that this energy may be understood as the gravitational potential energy of the planet, where the mass of the planet M is connected to its density and size in the usual way. For the Earth, this energy is around 10 to the 32nd joules, many orders of magnitude larger than the biggest bombs out there, which are merely in the megaton range. So this critical energy is quite out of reach. But if an unfathomable explosion of this magnitude was to occur, then the planet would be scattered to bits. That makes sense. Now, what if the explosion occurs on the surface? Based on our single example, the sedan test, we may assume for now that the radius of the crater is based on the energy and weight density. We call this radius R3. Just as for the underground cavity, this radius is bounded by the radius of the planet. Both radii are equal when the energy has the same critical value. Some astronomical bodies have come quite close to this dramatic fate. If we plot the three lengths we've seen against the energy of the explosion, the radius of the planet is independent of this energy. The radius of the underground cavity grows with the cubic root of the energy, and the surface crater as the fourth root. The three scalings intersect at the critical energy built solely from the elastic modulus and weight density of the planet, a material property of that planet if you wish. Above this limit, the whole planet is blown to pieces. Below, for a given energy, the radius of the surface crater is always bigger than that of the cavity. In fact, the radius of the crater is always a weighted geometric mean of the cavity radius and the planet radius. This is none other the mysterious four-dimensional geometric identity of our trio. In this idealized situation, it does not describe the shape of our crater, but it connects its radius to the radius of the planet on which it occurs, and to the radius of an underground cavity dug out by an explosion with the same yield. It connects three different but related objects: the crater, the cavity, and the planet. As we said in the previous episode, mechanical geometry is not solely about what is immediately apparent, like the shape of a three-dimensional object. Mechanics rather contextualizes geometry. It connects apparently different objects. These three objects and their lengths are literally connected, because at their intersection, the cavity, the crater, and the planet cease to have separate existences. All merge into the same bunch of rubbles. In this idealized example, the whole planet is made of a single material with an homogeneous density and elastic modulus. In practice, of course, this is not the case. The elastic modulus and density vary depending on the type of soil. For instance, if the explosion or impact occurs in alluvium, the density to consider is typically between 16 and 1800 kg per cubic meter, which is quite smaller than the average density of the whole Earth, around 5500 kg per cubic meter. Most types of soils found in the Earth's crust have densities smaller than the average, these examples in particular. These soils can be deformed in a number of ways, and for each type of deformation, a different elastic modulus could be defined. However, these moduli are usually of the same order of magnitude, so for our purpose here, we can forget about these subtleties and use the bulk modulus as a reference. For all these examples, the range of this modulus is also quite significantly lower than the average modulus of the entire Earth, which was around a few hundred gigapascals. For both the density and the modulus, the average properties of the Earth are quite skewed by its interior. The crust only represents about 1% of its volume. Nevertheless, the crust is where the impact and explosions we are interested in are happening. Let's start with underground cavities. Plotted here are the radii of the cavities created by a number of underground nuclear tests conducted by the United States. This radius is what we've been calling R2. The horizontal axis is the yield of the explosion, that is its energy E. It is here given in kilotons of TNT equivalent, but we can use the conventional joule as well. The color of each dot is related to the type of soil. Alluvium in yellow, tuff in red, and various hard rocks in black, like granite, dolomite, or sandstone. Evidently, larger explosions produce larger cavities. The two largest explosions, both slightly above 1 megaton, produced cavities around 100 meters in radius. Can we understand the size of these underground cavities as due to the balance between the energy E of the explosion and the elastic modulus sigma of the surrounding soil? The line drawn here corresponds to an elastic modulus of 3 gigapascals. Naturally, if we change the value of the modulus, we keep the slope, but we move the line up or down. This range between 1 and 10 gigapascals encompasses the elastic moduli of many types of rocks. the data do seem to fall in the vicinity of the path drawn by the power laws. However, to check the validity of the scaling more precisely, we can scale the cavity radius of each explosion by the simple length built from the energy and elasticity. The energy is known quite precisely, but the elastic modulus of the soil is much less constrained, bringing a non-negligible range of uncertainty to the scaled radius. If the radius of a cavity was precisely equal to the simple length built from the energy and bulk modulus, then the data points should be on the line of ordinate 1. However, as is often the case, the scaling actually includes a numerical correction, here around 1.7 on average. We added a little asterisk to the unit on the vertical axis to indicate that it takes into account the numerical factor. So overall, the radii of these underground cavities carved out by explosions do seem to broadly follow the scaling pairing energy and elastic modulus. Now let's investigate craters produced by explosions near the surface. The radius of these craters is what we've been calling R3. For a given energy, the radius of the crater is sensibly larger than the cavity that would be produced if the explosion had occurred sufficiently deep underground. Sedan, our example from earlier, is over here. If we focus on these craters, we may now ask if they follow the scaling, combining the energy of the explosion and the weight density of the soil. For each explosion, we know the energy and the density of the soil with some margin of uncertainty, so we can plot the crater radius scaled by the simple length combining energy and weight density. Here again, a better agreement between the data and the model is reached if we introduce a numerical factor, here around 1/2. In other words, the simple length on the right is a good estimate of the diameter of the crater, something we've seen already with the Sedan crater. On this plot, or on this one, the vertical axis is scaled. It uses objective units based on the mechanics, but the energy axis is not scaled objectively. It is given in arbitrary units. How can we compare these experimental plots with the little theoretical sketch from before? We've been focusing on 2 of these 3 lengths. If these 2 lengths follow the bare scalings, without any numerical prefactors, then they intersect at a critical energy given solely from the characteristic elasticity and weight density of the soil. We've used the subscript C for critical, but based on the way we've been using indices on this channel, we may as well use sigma and psi. Indeed, you can show as an exercise that this energy is the only energy depending solely on the elasticity and weight density. On the vertical axis, the bare scalings intersect at a critical length, also given by the same 2 mechanical factors. Now, what if the scalings include numerical corrections? We mentioned this issue in episode 9, but we did not get into the details. We need to be more cautious here. We invite you to equate both scalings at the intersection to derive that the critical energy in this case will include the following correction, and the critical size will also factor in the prefactors. Although the prefactors of the crater and cavity scalings are both of order 1, when they are combined to give the prefactor of the critical size and of the critical energy, they produce numbers quite significantly smaller than 1. So if these numerical corrections were to apply in our idealized testing ground, the cavities would end up being bigger than the craters when they are larger than about 1% of the radius of the planet, and for energies larger than about 2/1,000,000th of the gravitational binding energy of the planet. And so a range of energy above this limit could potentially be reached. For more realistic contexts, like that of cavities and craters in alluvium, the critical size and energy become even more reasonable. For instance, if the density is around 1.7 tons per cubic meter, multiplying by the standard acceleration of gravity on Earth, we get a weight density around 1.7 times 10 to the 4th Newton per cubic meter. Facing this weight density, if the elastic modulus is around 1 gigapascal, then the bare critical length is around 60 kilometers, and the energy around 2 times 10 to the 23rd joules. These numbers are still immense, but if we now take into account the numerical corrections, we get more sensible numbers. a critical radius around 600 meters, and a critical energy around 8 times 10 to the 16th joules, which is about 20 megatons of TNT equivalent, around the insane yield of the biggest nuclear bombs out there. We started with this plot, collecting the size of craters and underground cavities formed by various nuclear explosions in different types of soils. This plot uses standard but subjective units. If instead we use the mechanical quantities of the trio we believe to be relevant, then the plot can be given in objective units, where the numerical factors, the deltas, have been taken into account, hence the little asterisks on the units. If these numerical corrections were neglected, the horizontal axis would simply be the index of the trio. For all craters and cavities on this plot, the index is smaller than 1. What would happen if it were to be larger than 1? Would the craters start to scale like cavities? Would the other trend give information about the geometry of the craters? This crossover and the questions that it raises have been motivating research on craters since World War II. We hope to return to this topic in a future video, but we may already highlight a few points. For soils typical of the Earth crust, the critical energy can be in the megaton range and above. However, because of the way this critical energy scales with the elastic modulus and the weight density, it is easy to see that the right side of this plot can be reached at much more moderate energies if softer materials are selected, or under higher acceleration of gravity. The density is quite constrained and can't be changed much. Both lowering the elastic modulus and increasing the effective gravity by centrifugation have been and are still investigated. To conclude, we'll leave you with another important question related to cratering. So far we've distinguished crater and cavities as two clearly separate kinds. But this distinction is not as clear-cut. In fact, we may go from an underground cavity to a surface crater by changing the depth of the explosion. If the explosion is deep enough, we do not expect a crater, just a cavity. However, if the explosion occurs sufficiently close to the surface, we might observe some crater at the surface. Such so-called subsidence crater is typically due to the collapse of the roof of the underground cavity. Bringing the charge even closer to the surface may generate an even bigger crater. This illustration shows quite clearly how explosions with the same yield, here 1.2 kiloton, can yield significantly different craters, depending on the depth of the charge. How do you think these effects should be taken into account? We'll leave you with that. Thanks for watching.